Hello students, Assalamu alaikum and welcome back to my channel. Today I'm starting for the lecture voice viva also for the SS subject specialists in mathematics. So here I'm presenting some important topics related to functional analysis. That is, the first topic is norm spaces. Okay, so what do you know about a linear space? First of all, you should know about the linear space. Then after that, we will come towards the norm space. Okay, so what is linear space? So actually linear space, we mean that it is actually a vector space, and it is over a field F. Okay, field F is actually it is a field of real or complex numbers. Okay, so by it means that by linear space we shall always means vector space. And what is vector space? It is an algebraic expression. we जब हम लिखते हैं ना algebraic जो हम expression लिखते हैं प्लस एंड आल्सो मल्टीप्लिकेशन. ओके, तो विद रिस्पेक्ट टू डेट अगर ये फॉलोइंग प्रॉपर्टी सेटिस्फाई करते आई मीन डेट वी विद रिस्पेक्ट टू एडिशन, अगर ये बिलियन ग्रुप हो, बिलियन में ये 5 प्रॉपर्टीज आ जाता है ना कि वो कम्यूट करते हुए एसोसिएटिव प्रॉपर्टी, आइडेंटिटी, आल्सो इनवर्स एंड सो ऑन, ये सारे प्रॉपर्टीज़ जो है ये एक्सिम्स होल्ड करते हो तो ये बिलियन हमारे पास आ जाते हैं. ओके, इसके पास जो है और 5 प्रॉपर्टीज़ है वेक्टर स्पेस के. इसमें हमारे पास जो है अल्फ़ा बीटा अगर 2 स्केलर्स है जो कि फील्ड को बिलोंग करते हैं. ओके, और v1 v2 जो है वो v को बिलोंग करते हैं. तो ये हमारे पास क्या आ जाते हैं. और इससे रिलेटेड जो है फिर वो 5 प्रॉपर्टीज़ यू शुड नो अबाउट दैट. वो अगर फॉलो करते हैं, अगर होल्ड करते हो तो हमारे पास एक्चुअली क्या है, वेक्टर स्पेस है. तो दैट वेक्टर स्पेस एक्चुअली यहाँ पे लीनियर स्पेस ही आ जाता है. ओके, अच्छा, नाउ कमिंग टूवर्ड्स डिफाइंड नॉर्म एंड नॉर्म स्पेसेस. डिफाइंड नॉर्म एंड नॉर्म स्पेसेस. नाउ actually the topic is norm linear space, norm space. So you should know about the linear space, and after that you must know about norm space. So norm is actually a length of the vectors. Okay, so now towards the definition of the norm, coming towards the definition of the norm, that is, let n be a linear space. As you know norm, so it can be represented by n. So let n be a linear space over the field F, where field field हमारे पास जो है वो that is also complex का भी हो सकता है, real का भी हो सकता है. So that's why n(x) is a function. It is a function, and norm can be represented by the double lines. That is it is called norm. Okay, and the dot is actually for anything else. It is a representation of the norm. Okay, and it is a function of n to r and satisfying the following properties. So it is called norm space. Okay, first property is n1. For all x belong to n, x double mode, x norm is actually greater than or equal to 0, and और also हमारे पास जो है x norm is equal to 0. This implies if and only if x equal to 0, then this is the first property and it must be hold for the norm space. Okay, now coming towards n2, that is as any scalar, alpha is any scalar that is belongs to field, and x is any norm, x is any vector that belongs to norm space. So here if ax norm is equals to a into x norm for all a belongs to f and x belongs to n. As you know, as actually a scalar, so we can't use a norm abbreviation for this. We only abbreviated it in a simple mode, okay, modulus. Now coming towards n3, this is the third property, also called, we call it as a triangular property, and is also called triangular inequality, because there is inequality between these. As you know, x and y belongs to n. So if this property hold x plus y norm less than or equal to x norm plus y norm, so it's actually a triangular inequality. And if these three conditions hold, then it is called a linear space, okay. The pair this n and dot actually abbreviation for the norm space, where n is a linear space and this one is a norm defined on n, is called a norm linear space or simply a norm space, okay. So this is the definition. Now the question is, every norm linear space is a matrix space with the metric d n cross n that is mapping to R defined by this. So yes, the answer is actually, you know, as you know, the definition of matrix space, that dxy is equal to x minus y norm. In the form of norm linear space, it is the definition of the metric space, that is dfxy is equal to x minus y norm, okay. So it is the metric space in the form of norm linear space. Now the question is the norm function that is n2 are uniformly continuous? So yes, okay. This is the definition of the norm function, okay. Norm is actually norm of n is actually mapping on R, so it is a definition of norm function. And is it uniformly continuous? So yes, it is uniformly continuous, okay. All the properties of the uniform continuous hold for the norm function, so that's why yes. Now the question is, for a norm linear space and the function f n cross n that is mapping to n defined by this f of xy is equal to x plus y, where xy belongs to n. So here for this norm linear space, you know, this function n cross n, so it is actually uniform linear space, as both are the same, both functions are same. I mean, from n to n, the mapping is from n to n, so that's why these are uniformly continuous. And actually xy, there's an addition operation between the x and y, so that's why it is uniformly continuous. If we talk about the multiplication of the scalar with the any vector, so there will be only continuous, not at all uniformly continuous, okay. Now coming towards the next question, that is, for a norm linear space, the function, you know, f cross n that is mapping to n. Here f is a field, n is a norm, okay. So defined by, I mean that f cross n mean a, let a belongs to f and x belongs to n. So you know, g of x, for example, it is a function of a and x. So here we have a function that is x, so you know a is belongs to f and x belongs to n. So here f is in a field, okay. So it is a continuous, only continuous. Here the operation between the, I mean, scalar multiplication with any vector is actually only continuous, okay. So now coming towards the next question, that is, for a norm linear space in for any fixed scalar, the function that is, you know, function could be anything else. Here the function for the function h is all h is abbreviated, so h of n to n. It is a mapping of n to n defined by h of x is equal to x. So here is a function h of x is equal to x is yes continuous. So there is same question to the above first one, the previous question, that is these both are continuous because of this operation, because of scalar multiplication within vector. Which of them are true? So here that elements of the field will be called scalar. Yes, all the scalars actually belongs to field. Second one is -6 norm is actually x norm. Yes, because as you know, when we apply the second property, that is the second condition of the norm space, that is x norm is equal to actually here, as you know, minus, when we split the -1 from this, so -1 mode is actually one mode and one mode is actually 1 simply. So we ignore the one term, that is, and it gives us only x norm. Okay, the norm function, this is the norm function definition. Okay, so it is uniformly continuous. Yes, is from the above this one, you can say that it is uniformly continuous. Okay, from this definition. Now that here is the fourth one, that x norm minus y norm is actually less than x minus y norm. So yes, is actually the reverse process of this one, third condition of the triangular inequality. As you know, there is a addition operation and here is the negative operation, so you can reverse it, this third condition, and so this will become true. Okay, now every norm space is not a metric space. So no, every norm space, it must be a metric space, because that actually the definition of metric space related to the in the format of norm space is that d of xy is actually x minus y norm. So that here is the length here, as in metric space there is earlier there is talking about all about the length. So, and that norm is actually a length of vector. So yes, norm space is actually at metric space. So here it is false. Okay, now there is that some examples of the non-linear space. So that actually the linear space R space of real numbers and C space of complex numbers. That R is actually hold for the real number space and C space actually hold for the complex number space over themselves. So that there are some examples of the linear space. So the first one we always start from the real space, then after that we come towards the complex space. Okay, so these are the two basic examples for the non-linear space under the usual modulus norm. Okay, so and also if we take n tuples for the real space and also take n tuples for the complex space, then these are also the examples of the non-linear space. So here you can see that Rn and Cn, actually these are also the basic the second basic examples for the non-linear space under the norms defined as follows. Okay, so under these norms you can define Rn and Cn is like that. For Rn, as that it is taken from the real space, so here we take x in the form of x, and as C is a complex number, so here we take z terms. Okay, all the so as we always take complex numbers for the complex space, so here we always take real numbers, and here we always take complex numbers. So that in the form of this, when we defined Rn in the form of this, is a non-linear space xy mod square, and also take a square root from I is equal to 1 of 2 n. So it defines x Rn is a non-linear space, and it defines, when we replace xi by zi, so it defines complex space in the form of z. Okay, now coming towards the third example, that is in. Actually, what is in? It is a norm space. The space in is actually a norm space. It is a representation, and it is the representation of word term. So the elements of this space are elements of Rn, Rcn. So here in is actually belongs to the elements of Rn, Rcn. Okay, so you can take anything else from these two with norm defined these, or the norm defined for this in, that is x mod, x norm is actually supremum of the xi mod, where I is equal to 1 of 2 n. So it is the definition of the in. Okay, so this is also a norm linear space. Now the fourth one example is the space I infinity. Okay, here is in, that is finite terms, and here it is I infinity. It means that it is infinite term. These are infinite terms with the norm, and here you can see only this is n is replaced by the infinite term, so it is a norm linear space. These are all the norm linear space examples. Okay, the space C AB. This space CAB means that it consists of the all continuous real valued function which is defined on this AB. Okay, AB is an interval. Okay, and the C mean here is it show the continuity. Yeah, continuous valued function, continuous real valued function. Okay, we define the norm in continuous real valued function that is defined on EBR as f belong to this. Here actually real valued function is represented by the f norm, that is actually defined the supremum of the xi mod, where x belong to AB mod. AB actually here AB is the interval. Okay, so in a norm linear space. Okay, now what is n-dimensional Euclidean space? Now actually the examples become terminated. So now coming towards the next question, that is what is n-dimensional Euclidean space? Okay, the space Rn with the norm defined by this we put what is n-dimensional Euclidean space? Actually, what is Euclidean space? So Euclidean space is actually when when you take xi and also take a mod on this, then also take a square, and then summation from I is equal to 1 of 2 n, and take a square root on this, it is called Euclidean space. And if when we take a summation on this I from I is equal to 1 of 2 n, then it is converted from Euclidean space to n Euclidean space. Okay, n-dimensional Euclidean space. So here from I is equal to 1 of 2 n represent the n-dimensional. Okay, only Euclidean space definition is xi mod square and the square root on this. Okay, so it's called the n-dimensional Euclidean space. Now what is n-dimensional unitary space? Now here the only difference between the n-dimensional Euclidean space and n-dimensional unitary space is that only the xi term replaced by the zi term. Okay, here we take a space of R of n, about R of n, that is actually real number space. Okay, and here is the complex number space. Okay, so only xi will be replaced by the zi, so it will be, the definition will be converted from n-dimensional Euclidean space to n-dimensional unitary space. Okay, simple. And here as we take x from x1 x2 up to xn belongs to R of n, or here z is equal to z1 up to zn belongs to C of n. Okay, now define the space IP. What is IP? You will differentiate all these terms, that what is I and what is I infinity, what is IP. So this space consists of all the sequences. Here, we will take only as that here is here I, and that is, this is the I infinity. So these are the three different terms, and you must differentiate these. Okay, and there is so much difference between the ip, in, and I infinity. Okay, so ip is different from these two terms. So the definition is that it is consist of all the sequences x is equals to xn, where xn belongs to f, with the norm defined by, that is we will take xi, then xi mod, then a mod on this, and then we will take p on this mode. Okay, and then we will take a summation from I is equal to 1 up to infinity. Okay, then we take a square root, but square pth root with in the we will replace the square root by pth root. Okay, so here it is a pth root. Okay, and you know that this term is actually less than infinity. Okay, this is less than, because infinity term is very much bigger, so it must be less than infinity. So it is a definition of simple ip. Okay, so simply we can define is that this space consists of all the sequences. Okay, x, all the sequences, we represent sequences in the form of xn, or also take a braces on it. Okay, now what is ip is a norm space? Yes. So why we define it is a yes, because it is a norm space. So can we conclude I1, I2 spaces from IP space? Yes, as you know that when we replace p by 1, so here we will take 1, and here also we will take a 1. Also when we replace p by 2, then it will convert it in the form of 2. Okay, we also replace it by 3 and 4 up to n. Okay, so p can be replaced by anything else. Okay, so here I1 and I2 spaces also can conclude from the IP spaces. Okay, so now, as you know, there are different questions related to the functional analysis, and especially related to the nonlinear space. So we will continue it. So this is enough for today. Okay, take care, Allah Hafiz, and also subscribe my channel. Okay.